This is a recall question for part A, state the principle of moments. For 2 marks, first mark is the sum of the clockwise moments equals the sum of the anti-clockwise moments. Sum of the clockwise moments equals the sum of the anti-clockwise moments, in words obviously. And then your second mark is for an object in equilibrium, or for a system in equilibrium. That's the important word. Okay, then you get a description of a practical that you've probably done in class already, and you're using this equipment to find the mass or the weight of the rock here. You've got a plastic strip on this side, which is 0.2 newtons, at 80 centimetres. Now be careful, when I first looked at this question, I made the same mistake a lot of people do, and you think that that's your distance, and this is at 40 centimetres. But the pivot is at 50. So whenever you're thinking about moments, you've got to measure your distances from the pivot in the middle. So if the rock is at 40 centimetres, the pivot's at 50, that means that that distance there is going to be 10. And if your plastic strip's at 80, that means that that distance there is going to be 30 centimetres. So we'll just put those on there for later. So describe how the student can use an electrolytic balance to check that the plastic strip weighs 0.2 newtons. Now, you might think, why is that worth 2 marks? And it's because an electrolytic balance doesn't measure weight, it measures mass. And mass is in kilograms. So the first mark is for realising that. So it's a little bit of a trick question. So your electronic balance will give you your mass in kilograms. Then to turn that into a weight, you need to multiply by the 10 or 9.81 if you're feeling fancy, and then that will give you your weight. So that's how you can check that it's 0.2 newtons. Okay, suggest how the student could improve the precision of one of the measurements. So as soon as you see the word precision, you should think scale. So precision is all to do with the scale. So for a ruler, for example, you would improve the precision by switching from a centimetre scale to a millimetre scale. You would improve the precision of a balance by getting a balance that measures to more decimal places. So either of those examples there. The equation here, again, just a recall one, you need to know this. It's moment equals force times perpendicular distance. Again, write it out in words. There are no real acceptable symbols for that. And then use the principle of moments to calculate the force acting on the meter rule. So one of these 3 marks is for what we've already talked about here, which is realising that your distance on the anti-clockwise side is not 40, it's actually 10, and your distance on the clockwise side is 30 centimetres rather than 80. So that was what one of your marks was for automatically. So use the principle of moments. So we're going to start off with clockwise equals anti-clockwise. The clockwise force in this situation is your plastic strip, so 0.2 newtons, and it's 30 centimetres away. So we're going to do 0.2 newtons times 30 centimetres. It's fine to leave it in centimetres as long as it's centimetres on both sides, which it is. And then we've got the mass of the rock, which I'll just call R, and that's 10 centimetres away from the pivot. So if you work that through and rearrange it, you should end up with a force that is 0.6 newtons. Okay, so being realistic, suggest a reason why the weight of the rock will be different from your calculated force. Now that's 0.6 newtons when you look back at the practical equipment. It's not just the weight of the rock, it's the weight of the rock and the beaker. So that's why it's going to be different. You need to subtract the weight of the beaker from your calculated force.